Okay, I think everybody has taken a guess here. So once again, just to remind you, Alice, don't mix up Alice and Bob. Alice is betting all their money on one single coin flip, whereas Bob is spreading the money over 2 coin flips. Alice and Bob are both actually different versions of the binomial random variable. Actually, Alice, I guess, is double a binomial. So a binomial is the number of trials that you win. Bob did 2 trials, 2 coin flips, those are the 2 trials, and we call it a success if it comes up heads. So Bob really is a binomial, and Alice is double a binomial because she's betting $2. Her binomial is different though. Her binomial is only 1 trial. So this is what we're studying here. It's really secretly about binomials. And the nice thing is we can ask about the expected value and variance. These are the expected value and variance kind of tell you a lot of information. It condenses down the information into some small amount of numbers. Let's see what you guys said. Whose expected value is higher? Whose is lower? Okay, so the expected value, 25 people said Alice's is higher, and 15 people said Bob's is higher, 17 people said they are equal. So very split amongst everyone over here. For the variance, almost exactly split, where 25 to 27, Alice to Bob. So here's what I'm gonna do. I'm gonna write down the full distribution for Alice and Bob, their probabilities, and I'm gonna let you guys calculate. You'll really be able to calculate once I have the probabilities written down, and then we will have a calculation on whose is higher, and we'll revote then. So here is the calculation for Alice and Bob, if I can find the blackboard. And let us open a new page. So this is what we're gonna do. We're gonna find the expected value and variance for XA, which is Alice's winnings, versus XB, which is Bob's winnings. Okay, and Alice's is quite easy because I think I'm gonna do it with a tree. Either the coin flip comes up heads or it comes up tails. And when it comes up heads, then XA equals 2, Alice wins $2. And when it comes up tails, XA equals 0. So Alice, there can only be 2 things, either 0 or 2. And so I can put that on a nice we've been doing a little chart. So here's the value of X, and we have 0 or 2. Sometimes you could skip over 1, but to sort of make it fit into the same framework as Bob, I can write the probability. So the probability of getting 0, well, I just go down this branch of the tree over here, and so the probability is going to be 50%. 50%. Is this the right? I'm going to put a half for the probability. You can never be 0, or you can never win $1 if you're Alice, and the probability for 2 is a half. So there's Alice's thing. Really quite easy because there's only 1 coin flip. This could have been a question in the first few weeks of class. What is the only difference is we're giving it a random variable named XA. I guess we should say PA will be the probability for Alice. PA of X is the probability that capital XA equals lowercase x. There's our probability mass function for Alice. Questions or comments about Alice? Alice is easier than Bob. For Bob, you could remember that Bob is a binomial. So XB is a binomial. There's 2 coin flips, and the probability is a half. So there's 2 coin flips, and each of them is a half. Or you could sort of derive it from scratch. So you could do it like this and draw a little 2-layer tree, which isn't so bad in this situation. This is essentially how we handled the binomials. As we drew these little trees. If there's heads, then Bob will win $2. If it's heads, tails, then Bob will win $1. If it's tails, heads, then Bob will win $1. And if it's tails, tails, then Bob will win $0. And so we can make this, again, this nice little chart. I'm going to put it on the same chart as Alice over here so that they are on the same footing. For Bob to win $0, it has to go tails, tails. So that is a quarter chance because the things multiply. Things multiply. The probabilities multiply here by the multiplication rule and independence. Okay, and then, same thing with heads, heads, that's a quarter. So probability 1/4, Bob wins $2. And there's 2 different ways Bob can win $1. That's probability 1/2. And that really is we had this formula for n choose x times p to the x times 1 minus p to the n minus x. In this case, we're going to have a 2 choose 1 times a half to the 1 times 1/2 to the 1. That is this number 1/2 over there. It's a quarter, but then times this 2 choose 1. This is all kind of review from our binomial days. But however you do it, you should get this little table for Alice's and Bob's distribution function. And once you've done this step, which isn't so hard, now it really is just a calculation. Find the expected value. Any questions or comments about this, how I got these numbers? I think if you've been following along, it's pretty straightforward. But if you you were asleep on the day we did what is p, then this doesn't make any sense. Questions? Okay, so now you have this. Let's calculate again the expected value and the variance. So let's find the expected value of xa. It should be an honest to goodness number. And the expected value of xb, it should be an honest to goodness number. And then we're also going to do the variance of xa, and the variance of xb. Let's do the expected value first. So I'm going to have you guys work out the expected value, figure out these two numbers. It's a great question, the kind of thing that might be on the midterm. And I will put a mathematize up that says, you tell me these two values. And then we will see, are they equal or not? And then in a minute, we're going to do the variance as well. But I will get you started. Here is a little timer to get you started. Calculate the expected value for each. And then if you finish early, start doing the variance, because that will be coming up. OK. I will set you loose to do that while I create the mathematized question. OK, here is the mathematized question, asking you to put in what you got for the expected value for Alice and Bob, respectively. This is answering the question, how much money do they make on average? And that's our first question. Let me start the timer here for 1 minute. Hopefully, you have already worked out the answer, and you just have to type in your answer. OK. All right, let's see what people said. Alice and Bob. Who is making more money? OK. 40 people think Alice makes $1 on average out of 49. Huge majority on $1 for Alice. What about Bob? Also, huge majority on 1. Slightly smaller than before. Some interesting answers over here. But 1 is the correct answer for both. So if you got those right, most people did. Very nice job. Let's see how you would do it in case you were confused. And the thing you do if you have a little table like this is you can calculate. Let's see, do I have a highlighter? Yeah, zoom out one. Okay, man, I don't zoom out. I don't know. I don't have a highlighter. Okay. So you take the probability and you multiply it by the value, and you take the probability and you multiply it by the value, and you add these all up. So you're doing these two numbers combined. In Excel, there's a function called sum product. That's what we're doing. So it's 1/2 times 0 plus 1 times plus 0 times 1. 0 times 1 plus 1/2 times 2. That is Alice's answer over here, right? So half probability times a chance of 0, a 0 probability times a chance of 1, and a half probability times 2. You add up all the values times the probabilities, and you get a half times 2 plus 0, which equals 1. So there's Alice. And let's do Bob. Let's move Bob down a little bit so we have a little more space. Oh, I took the bottom of the 1. Okay. Come back 1. Okay, so that was Alice. Bob, a little more complicated, but same kind of thing. You do a quarter chance of 0 plus a 1/2 chance of 1 plus a quarter chance of 2. So even though Bob's is more spread out, you only have a 1/4 chance of getting $2, whereas Alice had a 1/2 chance of getting $2. So this is ending up with a half from the 1 plus another half from the 2, which also equals 1. So both Alice and Bob, on average, make $1. This is, I think, the first kind of thing, the intuition. If you're placing bets, and you can place all your bets on one thing, or you can spread your bets out, on average, it makes no difference. So averages are kind of linear. Betting on something and betting on something else is the same as putting all your money on one of them. So a lot of people were split before, but now you see that they should have the same average. And if you kind of get the feel of these averages, it kind of intuitively makes sense. I will say, not only can you do it intuitively, but you can use it, you can prove it mathematically rigorously using a fact that was mentioned in the video many weeks ago, which is expectations are linear. Are linear. And expectations are linear means two things. The expected value of the sum of any two variables. What should I call my two variables today? Let's call them x and y. So if you want to do the sum of x and y, that's the same as doing the expected value of x plus the expected value of y. So be careful. It doesn't work for squares and other things, but it does work for linear. Linear means plus and scalar multiplication. So there's the plus rule for adding things. And there's also the scalar multiplication rule, which says the expected value of c times x equals c times the expected value of x, where c is non-random, a constant. Okay, why is this useful? This seems very abstract. Does this have anything to do with our problem? Well, yes, it does. We could have, in addition to calculating it the way we did, which is kind of the slog through the whole table, it's a good skill to have, and sometimes that's the only way to do it. But we could have done it a sneaky way. So here's the sneaky way. Alice's winnings are actually their XA, it is 2 times what I call an indicator random variable for heads, where the indicator for heads is either 1 or 0 if it's heads or not, if tails. And because Alice is double something, right? You either win the coin flip or you don't, and we multiply it by 2. Therefore, by the rule, if I do the average of what Alice won, that is the twice this indicator, and by the scalar multiplication rule, this equals twice the expected value of this one coin flip. So these i's, I stands for indicator. We saw it a few classes ago. There are these random variables that are either 1 or 0. And what is an indicator on average? Well, that's actually quite easy. So the expected value of an indicator is, in this case, well, half the time it's 1, and half the time it's 0. So very simple. This is equal to a half. And so this is 2 times 1/2, which equals 1. So by using the scalar multiplication rule, I can turn Alice's thing into just understanding this simple thing. All right, that was maybe a lot of work for Alice, but for Bob, it's even better. So for Bob's winnings, they are the sum of two different things. XB is the indicator of heads number 1, I'm going to call it heads 1, plus the indicator of heads number 2, heads 2. And therefore, if I take the average of what Bob won, it is the sum of these two things. And by the addition rule for expected values, this will split up. So this will be the expected value of the first one plus the expected value of the second one. So this will be 1/2 plus 1/2. All right, so now you can kind of see why are Alice and Bob the same? Well, Alice is getting double the expected value, and Bob is getting the sum of two different expected values. But of course, that's the exact same thing. So Alice and Bob are doing the same thing, and this linearity rule is explaining, it's one explanation of why they have the same mean. I can barely fit both of them onto the same thing. So we could have calculated it by hand and seen they were both 1, or we could have seen in general they must always be equal in this kind of situation. Questions or comments about that one? Yeah. Yes. What does plus mean? Well, okay. So look, this little description of add them together is exactly what was given to you in the mathematized problem, right? So remember our original mathematized problem said Bob spreads his bet out over 2 coin flips. On each flip, he wins $1 if it comes up heads and 0 otherwise. This description is I heads 1 and I heads 2, right? I heads 1 says 1 if it's a heads and 0 if it's not. And there's the first flip and the second flip. And then it says his total winnings is the sum of the 2 flips. So what I've done is I've taken this text and I have converted it into random variables. And I've said Bob's winning X is equal to what he won on the first head plus what he won on the second head. What he won on the first head and what he won on the second head were either 1 or 0. It's true. It's kind of like when you first see the stuff, maybe it's a little jarring. Like, what do you mean? Like, what do you mean? How can you write it as a sum? But it's literally just what it was in words before. I will say we sort of got around it before by using a probability tree to figure out what the outcome was. And you're probably just more used to that because we did it in the first few weeks of the class. But it's the same. It's another way of figuring out the same thing, which is this binomial random variable. You can write a binomial random variable as the result of a big tree, or you can write it as the sum of some smaller random variables like this. Both are equally good ways to represent it. You could also directly go to this formula with the n choose x. That would be another valid way. All different ways of thinking about the same thing. Yeah. There are shortcuts, and in some situations, the shortcut can be a lot easier or harder. And that's why we want to show you both ways. Yeah, great question. Anyone else? All right, we're actually here at a perfect little fact. We have actually, by doing this work over here, we have basically proven the following fact about binomial random variables. This is a binomial fact, which is if x is a binomial of n trials, each of which have probability p, right? So n trials, each is probability p. Then, what is x on average? And I think we mentioned this result, but we didn't explain why it was true or why it would be useful. But in fact, we have proven it in this little thing. The average is n times p. Okay, and here is the proof. What is the proof? The proof is to write x as a sum of indicators. It's I1 plus I2 plus ... plus In, where each I is either 1 or 0 with probability p. Let's see, with probab p and with probability 1 minus p, right? So the idea is you can think of the binomial random variable as the big tree, or just the probabilities in terms of those binomial coefficients, those n choose x's. But as a random variable, we can write it as a sum of these indicators. And now by the linearity, we can take the expected value. And so we get the expected value of this big sum, I1 plus ... plus In. And now we can use linearity. Use plus linearity. So the rule we just saw, it's I1 plus ... plus plus the expected value of in, which is there's n copies. We're adding up the same number n times, and that number is the average of I1. The average of I1 we can easily figure out. It's a 1 with probability p plus 0 with probability 1 minus p, which is also known as p. So this is p plus p plus p plus dot 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 plus p n times, also known as n times p. Adding up the same number n times is the same as multiplying by n. So this is the average of a binomial random variable, and if you kind of know this trick of using linearity, it's very simple. If you don't know the trick, it's quite complicated. If you don't know the trick and you try to add up the distribution, then you got to be really good at adding stuff. You can do it. You need to know some combinatorics tricks. But that is the proof that of the mean of a binomial. And you can see that the difference between Alice and Bob is basically Bob has a higher n, and Alice only has 1 point. But they have the same average. So there we go. OK, questions or comments about averages? We're about to move into variances, which are like averages on steroids. So as if there's something I can clarify now about the averages, I'm happy to do it. OK, let's go. Let's do the variance next. And so we're going to try to fill in this question. What is the variance of Alice and the variance of Bob? We're going to start by doing it using the little table. And it will help you to know that the average is 1. So the average for both Alice and Bob was 1. That is a useful fact. When you go to calculate the variance, I think the easiest formula here that we can use is the formula from last class, that the variance of some random variable is the average of that random variable squared minus its mean squared. And in this case, the mean is 1, so you're going to calculate the expected value of how much money Alice and Bob win squared, and then subtract 1. Okay? So that's what I'm going to have you try to do. If you followed along with the calculation from Monday's class, is another calculation like that, except there's only like 3 little values. Questions about how to do this one? OK, let me set you loose. Again, we're going to have a nice little mathematize here, where you can tell me what you think the variance is. So that is open in mathematize, but I will leave this on the board for a little bit, and then maybe in the last 30 seconds I will bring that up. You can always, if you know the code, then you can go and do that. Let me give, let's say, 2 minutes and 30 seconds for all this. OK, there's 30 seconds left. Here's the mathematize. If you haven't put in your answer yet, put in what you think it will be. Okay, time's up. Put in your guesses. Yeah, once again, if you're not used to calculating the variance and you're like struggling on, oh, where do I start? Then this can take a long time. If you know how to calculate the variance, you know how to do these expected values from the table, it's very quick, right? So maybe the hard part is knowing what to do. Once you know how to do it, it's not so bad. I think in this case, because we want to do the expected value of x squared, I'm going to add a little x squared column or row on my table. So if x is either 0, 1, or 2, then what is x squared? Well, it's either 0, 1, or 4, you see? And then now I have the probabilities, and I have the value of x squared. What is the expected value of x squared? You go over all the probabilities, and you multiply by the x squared value. So for xa, there's a 50% chance, a 1/2 chance times 0. Okay, that's very nice. 1/2 times 0. Then there's a 0 times 1. That's very nice. Plus 0 times 1. And then this is where maybe it gets spicy, 1/2 times 4. Right? So if you forgot that 4, you would be in trouble. And that's the only difference between the expected value and the variance. When you're doing the expected value squared, you square all these values. So instead of being 0, 1, 2, it's 0, 1, 4. If there was 3 and 5 and so on, you have to square those numbers. You'd get 9, 16, 25, etc. Okay, what I wrote down is not quite the variance. Does anyone see what I'm missing over here? I wrote the expected value squared. What did I forget? What was that? The m, the mu. The mu. Yes, so I got to subtract 1, minus 1 squared. So don't forget, the variance is not just the thing in the red over here. This is the expected value of the value squared, but I have to subtract 1 because the variance is not just the expected value squared. It's the expected value squared minus the mean squared, and the mean was 1. So what is this all together? You get 0 plus 0. 1/2 times 4 is 2, so it's 2 minus 1, also known as 1. Look at that. Nice value for the variance, which is 1. That's the variance of Alice. Okay, let's see what people said, actually. Did people get the variance of Alice? Okay, 28 people got it right. That's very good. 16 people are confused, but maybe now that they've seen it, it will be okay. If you said 2, then you probably did it correctly and you just forgot to subtract 1. So actually, this is pretty good. Okay, what about the variance for Bob? And remember, we worked out, right? We had Alice and Bob. They're betting on the same kind of coin flips, and Alice bet all her money on 1 flip. Bob spread out the bets on 2 flips. The averages were the same. What about the variances? Are the variances the same? Well, let's see what you guys calculated. And in this one, okay, this one's more split. 0, 1, 2, 3, does not exist. 0.5, and I believe 0.5 is the right answer. So if you put 0.5 for Bob, that is correct. Let's do this one. It's the same kind of calculation as before that you should become fluent with. Okay, so for Bob, it's a little trickier. It's 1/4 times 0 plus 1/2 times 1 plus 1/4 times 4, and then with the same minus 1 at the end, minus 1 squared. And now when you add these numbers up, 1/4 times 0 is 0, 1/2 times 1 is 1/2, plus 1/4 times 4 is 1. So this is 1.5 over here. So let's say 1/2 plus 1, and then minus 1 equals 1/2 as the final answer. So even though the averages are the same, the variances are not the same. This is the difference between Alice and Bob. They have the same, on average, they win the same amount of money, but their bets are different because they have different variances. And remember, we said that variance is kind of a measure of, this is an idea. Variance is a measure of variability. Variance measures variability. Right? So the fact that Alice has a variance of 1 and Bob has a variance of 1/2 is kind of the idea that Alice's bet is a riskier bet. It has more variability. It could either work out really well for her or really bad for her, whereas Bob's bet is more spread out, is more subdued. Kind of most of the time, it works out close to the average. And indeed, that kind of makes sense, right? Like Alice is going all in on one single bet. She's going to win it all or lose it all, whereas Bob actually half the time does, wins exactly $1, wins 1 out of 2. So Bob is less variable, whereas Alice is more variable. Okay.
Professor Nika, I'll make
yes,
an interjection here.
Yeah.
This is something I've seen from many students taking probability. A common misconception when looking at variance and just looking at the numbers is to think Alice's are less variable because she can only get a 0 or a 2 as her outcomes, whereas Bob gets a 0, 1, or 2 as their outcomes. So Bob has more possible outcomes than Alice does. So doesn't that make Bob's outcomes more variable? Well, that's not what we mean by variability. And we get back to that idea of variability, the average squared deviation about the mean. I know that's a weird thing to kind of think about, but for Bob, half the time he gets a winning of 1, and the mean is 1. So there's no variability about that mean. The only values that could vary about that mean are either the 0 or the 2, whereas Alice never hits the mean, right? Alice can't win exactly $1, and in fact, the 0 and 2 are spread away from that mean as far as possible, at least as far as possible with respect to the way the game is played. So again, just try to emphasize, don't just think about it as the number of possible values that come out. You're looking at how individual values are weighted towards their distance from the mean. And it's by distance from the mean, it's actually squared distance from the mean, which is,
yes,
it is the way it is.
Yes. I guess a good question to ask. Here's a question. Why do statisticians care so much about variance? Why do statisticians care so much about variance? And I have two answers. So answer number one is it's actually easy, relatively speaking, easy, relatively, to calculate. And two is it controls how far things are from the mean. Okay. This is why we care about variance so much. Easy to calculate. You just saw having to do it sort of by hand, like this, is a big slog. But just like the expected value is linear, the variance also satisfies some nice properties that are a little bit like this. And those properties make it easy to calculate variance. So let me show you the easy way to calculate, just like we had an easy way to calculate the variance. So here is the fact about variance. The important thing is this does not always work. It only works if x and y are independent. So let me write down this one. If x and y are independent, and this is absolutely crucial, if they're not independent, this is not true, then the variance adds. So the variance of x plus y equals the variance of x plus the variance of y. So for independent sums, if the two random variables are independent, if the probability of one does not affect the probability of the other, then you can add the variances. And this makes it a really easy to calculate this kind of thing. So we'll go back and we'll do Bob's variance calculation with this. And there's also a similar fact for scalar multiplication. So this is the plus fact. And here's the other fact. If c is a constant, then what is the variance of c times x? A lot of people get this one wrong, and they think, oh, it should be like the expected value. You pull the c out. But actually, it pulls out with a square. So it's c squared times the variance of x. So variance is, I like to think of it as variance is square e. Square e. The proper term is that it's a bilinear form. This is the proper math term. You don't need to know this. A bilinear form. But it behaves like the square. Okay, that's very nice. Why is this useful? We can calculate Alice's and Bob's. So here is the shortcut calculation for Alice and Bob. The shortcut for Alice and Bob. So remember, Alice is double a single coin flip, and therefore the variance of Alice is the variance of double a single coin flip. And this time it pulls out with a factor of 4, right? So don't pull out the 2, you pull out a 4. The 4 times the variance of a single coin flip. And then you got to work out what the variance of a single coin flip is. But remember, a single coin flip is quite easy. So it's either 0 or 1 with probabilities 1/2. So there's x and p of x. And so the variance of a single coin flip, the mean is 1/2, and the expected value of x squared is also 1/2. And so the variance is 1/2 minus 1/2 squared, also known as 1/2 times 1 minus 1/2, also known as a quarter. So Alice gets 4 times a quarter, which is 1. That is the same as what we calculated before, but this is a sort of a shortcut way to do it. You might think, whoa, man, this is way more work. And indeed, for this very simple example with only one single coin flip, it is kind of more work, but we're going to see the general formula for the binomial. You can get the formula for the variance of the binomial for any number of coin flips and any probability. Okay, that was Alice. Let's do the same shortcut with Bob. Remember, Bob is I1 plus I2, right? And so what is the variance of Bob? It's the variance of the first coin flip plus the second coin flip. And because these two coin flips are independent, what happens on the first coin flip doesn't affect the second one. You can add the variances. I1 plus the variance of I2. And they're both individually a quarter. A quarter plus a quarter. Also known as a half. So that's the same answer as we got before, but the kind of doing it the easy way using the properties of variance. This is why statisticians love variance. You can calculate very quickly by using these tricks. In particular, it plays really nice with independent random variables and sums and things like that. You can also see from this calculation why Alice has more variance than Bob, right? Bob is the sum of two things, but Alice gets the square factor. So when she bets $2 on something, she's not multiplying her variance by 2, she's multiplying her variance by 4. Doubling your bet multiplies your variance by 4, not by 2. Yes?
So the variance of x there,
Yeah.
was x the number of heads or the winnings?
Well, we said they get $2 if they win, and they get $0 if they lose. So they've sort of already paid their fee to enter the casino. And yeah.
So why does XA have a lower variance?
XA has a higher variance. The variance of XA is 1, and the variance
you
of
got
XB
it up
is a
there.
half. Maybe
you got it up there.
You got
okay.
A and B
yeah,
mixed up.
I missed it. You got that up there.
All right. Yes.
Yeah.
Okay, good. I mean, it could have equally well been me that switched the lanes.
I was
this
just
is
reading
what
the
we calculated by
bottom.
hand.
I was reading the bottom, missed
Yeah.
the top up there.
Okay. So this is the shortcut way to calculate Alice and Bob's variance. And actually, this leads us, just like we had a general fact, there's a general fact about binomials. If for a general binomial random variable, a binomial of n and p, what is its variance? The variance of x. It's the following. It's n times p times 1 minus p. And the proof is very similar to before. So you write x as I1 plus ... plus In, and then the variance of x is the variance of all these things. And now, by the linearity, this is the variance of each of them. The variance of I1 plus the variance of I2 plus ... plus the variance of In. And now we have adding up the variance of all the individual coin flips. Each individual coin flip is either 1 or 0. So the values are either 0 or 1. And the p-values are p and 1 minus p. This is an individual coin flip. So each of these individual coin flips is either 0 or 1. You can quickly calculate the variance of one of these coin flips.
Professor Nika, do you want the 0 1s the other way around? The p's and 1 minus
Oh,
p?
I do. Yes, that's a good point. Okay, very good. It has a probability p chance to be 1 and a probability 1 minus p chance to be the other way. Okay, 1 minus p and p. Okay, so yeah, we should do the expected value of x squared minus the expected value of x squared. The expected value of x squared, well, when you square 0 and 1, you get 0 and 1 again. So there's a 1 minus p chance to being 0 plus a p chance of being 1 minus the expected value is the same kind of thing, all squared. If you did it correctly, you should end up with p minus p squared, also known as p times 1 minus p. This is very similar to what we did before. Before p was a half, and we had a half times 1 minus a half. Now it's p times 1 minus p. Okay, in any case, you're adding up the same number a bunch of times, p times 1 minus p, plus p times 1 minus p, plus dot dot dot, plus p times 1 minus p. And this is n times p times 1 minus p, which is the variance that we wanted. There we go. So what is the moral of the story? Variance is nice because it has these nice rules, and that lets you do really complicated calculations that would otherwise take you all day and be extremely hard to do. You can do them by using these nice properties. And we've seen it for Alice and Bob. Last but not least, I'm going to circle back to the second bullet point. It controls how far things are from the mean. We won't get into this specifically, but let me show you a nice little picture of what's going on here. So this plot we had for, this is the binomial distribution, and I can put in the n value and the p value over here. So let's put in p equals 0.5, and let's put in n equals 2. This is Bob, right? This is Bob has a 50% chance of winning 1 coin flip and a 25% chance of winning 2 coin flips. But let's make it a little more exciting. Let's do 10 coin flips. So there's Bob. Or I guess this is Charlie. Charlie bets on 10 different coin flips. Most of the time, he wins half the coin flips, but sometimes he wins a lot, or sometimes he loses a lot. And what am I trying to show you on this? Well, the mean is in the middle. So the mean is p times n, if that's in the middle. And the variance will tell you how far above and below the mean most of the distribution lives in. And I've drawn that on here with a plus and a minus. Let me draw these two things in. Here's one of them. Where are they? Mean, oh, I have to open this up. Okay, here we go. Mean plus, so there you go. This is the mean plus 1 standard deviation. The standard deviation is the square root of the variance. This is the mean minus 1 standard deviation. And there are theorems you can prove in probability. We're not going to prove them here for you, but if you continue to take courses, you will learn them. That say most of the time, it has to be in this little window. It cannot be too far away from the mean. It has to be contained in this window, centered around the mean, and whose width is the standard deviation. And to check that this is true, we can change the p-value and the n-value here. Why don't I try to make this like 40? And I can change the p-value, and you'll see that even when the p-value changes, most of the time, no matter what you do, most of the time, most of the mass there lives there. So without having to calculate all these n choose k's and things like that to get the exact probability distribution, I can say things like most of the time, it's going to be in this little region. That's why the mean and the variance are so powerful, and that's why we like them so much. Okay, I think we're going to leave it there. We'll see everyone on Friday. If you have questions or comments, please come up.
Quick announcement,
Yeah. I can do that. Yes.
Just let me get a quick announcement in before everybody leaves. Later today, there are going to be practice problems for test 2 going up, okay? And solutions.